Okay, good day. So let's have another example for the design and analysis of a simple connection for a steel design. So for this example, okay, so how many 19 millimeters diameter A325 bolts are required for the bearing type connection shown if so you have a dead load of 200 kilonewtons and a live load of 400 kilonewtons. So we are to use A36 steel. So let's say the Fy is equal to 248 megapascals and the F sub U is equal to 400 megapascals. And we are to use both methods, so the LRFD and the ASD. So assumed threads are excluded from the shear planes. So this is our connections, and we are to use plates 16 millimeters thick and 300 millimeters wide. So we have this spacing, we have 50 mm from the edge of each plate to the center of this bolt. Then center to center distance of the bolt will be 75 millimeters. Okay, so if you are to go back on our reference, okay, so let's try first the bearing strength. Okay, so for the bearing strength, again, so we have three conditions. But okay, for this problem, it is not indicated if we are to assume if deformation is a consideration for the design. But I think that is ideal that we should consider deformation as a design consideration. So therefore, I will be using this equation. Okay, for the reaction, or that is the R sub n, the load to be carried by one bolt. Okay, so let's start with our solution with first. Okay, let's have our P sub U. So the P sub U is equal to the 1.2 of the dead load, plus the 1.6 of the live load. That is equal to, we have 1.2 of 200 kilonewtons, plus the 1.6 of 400 kilonewtons. And this is equal to, we have a 1.2 of 200 kilonewtons plus the 1.6 of 400 kN. Okay, so we have 800. This is 880 kilonewtons. So this is for the obviously for the LRFD. Okay, then for the ASD, that is the P sub A. So that is basically the dead load plus the live load. So this is equal to 200 kilonewtons plus the live load is 400 kilonewtons, so a total of 600 kN. And this is for the ASD. Okay, let's have first. So again, we proceed to the bearing strength of one bolt. Okay, so for the bearing strength of one bolt, so again, we are using the first condition. Okay, we have that as the R sub n is equal to 1.2 of the LC or L sub C multiplied by the thickness of the plate or multiplied by the value of the F sub U. But this value should be less than or equal to 2.4 or multiplied by the diameter of the bolt, then multiplied by the plate thickness, multiplied by the F sub U. Okay, so for this condition, we need to determine first the value of the L sub C. So we have again two possible values of L sub C. So this will be the first one, first consideration for the L sub C. Let's say L sub C number 1. So what is the value of L sub C number 1? Again, we are using a 19 millimeters diameter bolt. So, okay. So the diameter of the bolt, the diameter of the bolt is equal to 19 mm. So the expected diameter of the hole will be equal to 19 millimeters plus 2. This is equal to 21 millimeters. But again, based on our NSCP, we will be having a net diameter of the hole as from 21 millimeters plus another 2 mm. So we'll be using diameter of the net diameter of the hole to be 23 millimeters. So how do we compute now for the value of L sub C? L sub C1, that is 50 mm minus half of the diameter of this the net diameter of the hole. So we'll be having, we have L sub C1 is equal to, that is 50 mm. So from the edge of the plate to the center of this bolt, then we are to subtract, since that is up to the center, we are to subtract half of the diameter of the hole. So that is minus the 1/2 of 23 mm. So we'll be having a value of L sub C1. This is 50 less 0.5 of 23. Okay, that is equal to, we have that as 38 point. This is 38.5 mm. So we need to consider another value of L sub C, a bearing length. So the other bearing length is the center to center distance of the bolts. Let's say this is our L sub C number 2. So the center to center distance is equal to 75 millimeters. Then we need to subtract, so 1/2 of the diameter of the hole on this side, then another 1/2. Or basically, that is 75 millimeters, minus 1/2, that is minus 1 net diameter of the hole. So let's say this is our L sub C number 2. So again, that is 75 millimeters minus 1/2, or that is the same as 1 net diameter of the hole minus 23. So 75 minus 23 is equal to, this is 52 mm. And we are to adopt the lesser value of L sub C. Therefore, we are using 38.5 mm. So let us now compare these values when it comes to the bearing strength. This is the R sub N is equal to 1.2. Again, our L sub C is 38.5 millimeters. The thickness of the plate is given as 16 mm. Then the value of F sub U is equal to 400 megapascals. This is in newtons. So this value is in newtons. So we are to divide this value by 1000 newtons. And again, it should be less than or equal to 2.4. The diameter of the bolt to be used is 19 mm. The thickness of the plate is, we have that as 16 millimeters, and F sub U is 400 mm. Also, in newtons, so to be divided by 1000 newtons. So that our values will be in kilo newtons. So let's have the value of R sub N. This is 1.2 multiplied by the 38.5 millimeters, then multiplied by 16, then 400 megapascals. Then to be divided by 1000. This is 295.68 kilo newtons. And is it less than or equal to the values of the right side? This is 2.4 of 19 millimeters, then 16 mm by 400. And it should be divided by 1000. So 291.84. So this is 291.84 ay kilonewtons. So 291.84 kilonewtons. So therefore, this condition is not satisfied. So therefore, we are to use our limit. The R sub n is equal to, so we'll be using the lesser value. 291.84 kilonewtons. So let us consider. So after the bearing strength, so when it comes to the bearing type of connection, let us consider the next one. This is the shearing strength. So let's say this is the shearing strength of 1 bolt. So take note that this, when it comes to the bearing strength of 1 bolt, this 291.84 kilonewtons is again per bolt. So the same with this one. This is R sub n is equal to m, then multiplied by the F sub n b, multiplied by the area of 1 bolt. So we'll be just using this formula R sub n equal to m F sub n b a sub b. Okay, since we are looking for the number of bolts, and our analysis is again per 1 bolt. Okay, so again, by definition, what is the value of m? The value of m is the number of shear planes, but based on our connection, per bolt we have only one shear plane, so that is basically equal to 1. Okay, so we have based on the given, we are using again, I think, from the previous example, we are using A325 bolts. So when it comes to A325 bolts, based on our NSCP 2015. So NSCP 2015, this is on page 5-99, and we are using table. That is table 510.3.2. Okay. So since on this, since it is indicated on this problem that threads are excluded from the shear plane, so therefore again we are using F sub nb equal to 457 megapascals. So again, kindly refer this value on our reference. Okay, so what will be the shearing strength capacity of 1 bolt? This is, we have R sub n, so the number of shear plane is only 1. F sub nb is equal to 457 megapascals, or the newtons per square mm. Again, we are using a 19 mm diameter bolt, so its cross-sectional area will be equal to 19 squared pi divided by 4. And obviously, this is in terms of the square millimeters. So for the value of R sub n to be in kilonewtons, this value to be divided by 1,000 newtons. So we'll be having the value of R sub n is now equal to 457 multiplied by 19 squared, and then shape pi over 4. Then to be divided by 1,000 to be in kilonewtons. That is 129.57. 129.57 kilonewtons. Now we need to compare these two. So again, this is the shear strength per 1 bolt. Okay, so we are now to compare the shear strength and the bearing strength of 1 bolt. So for the bearing strength, that is 291.84, and shearing strength of 1 bolt is 129.50. So that is the 129.57 kilonewtons. So we are to adapt 129.57. So again, when it comes, if we are designing So the weaker force is the safer force. Or this is our design value. Okay, 129.57 kilonewtons. So when it comes to the LRFD, okay, so for our design, this is LRFD. Okay, so we have the P of R sub n is equal to, or is equal to the value of P sub u. So LRFD, our reduction factor P is equal to 0.75. So let us now determine the number of bolts needed. To be more specific, okay, so this is the capacity of 1 bolt is 129.57. I will be using this value. Again, the smaller value will control the design. So we are using the R sub n equal to 129.57 kilo newtons. This is per bolt. So we are to equate the total capacity of the bolts. Let's say this is P of R sub n multiplied by the number of bolts. That will be the total strength of all bolts is equal to the total the ultimate load P sub u. So again, what is our P sub u? So earlier we have that value as for the value of P sub u is equal to 880 kilonewtons. So we have reduction factor P is equal to 0.75 for LRFD. Okay, multiplied by R sub n is 129.57. Then to be multiplied by the number of bolts is equal to P sub u, that is equal to 880 kilo newtons. Okay, so let us now compute. So what will be the required number of bolts for LRFD? Okay, so this will be equal to 880 kilonewtons to be divided by 0.75 of 129.57. That is 9.06. But for us to increase the factor of safety, we may use, let's say, we are using 10 bolts. Okay, then when it comes to the ASD, so for the ASD, our factor of safety is equal to 2.00. So for the allowable value of the load to be carried by this connection, that is the R sub n divided by the factor of safety. But the equivalent of the total allowable strength, that is to be multiplied by the number of bolts. And this should be equal to the allowable load. Okay, that is the same as the value of the P sub A. So a while ago, what is the value of our P sub A? That is 200 plus 400. So we have that as the 600 kilo newtons. So let us now determine the required number of bolts under ASD. So our R sub n is equal to 129.57 divided by the factor of safety is 2.00 multiplied by the number of bolts is equal to our allowable load is 600 kilo newtons. So so for the number of bolts under ASD, is equal to, so this is 600 times 2, then to be divided by 129.57. That is, let's say 9.26. Again, we don't have a 9.26 bolts. So we are using 10 bolts. So the same answer as the LRFD. Okay, so for both methods, okay, we may conclude that we are to use 10 bolts. So these bolts are A325 bolts. Okay, so this will be our solution and answer, okay, for this example.